Let's have a look at this tricky integral from 0 to half pi x over tangent x dx. First, let's observe it. So can we use maybe trig substitution? Doesn't look like so, because there's no radicals, no squares, no 1 plus something square under square root. And then is it possible for us to use integration by parts? Right? If we treat, I don't know, if we want to find out derivative of 1 over tangent x, then that's going to be hard to find. And if we want to find out antiderivative of x, right, that's going to be easy. But if we want to differentiate 1 over tangent x, it's going to be not that easy. So that's going to even make the problem even more complex. So here's the strategy. So first, let me use tangent x substitution equals theta, perhaps equal t. So therefore, x as the angle, t is the trig value. So in other words, arc. So x should be equal to arc tangent of t. Right? So the dx becomes just standard derivative, 1 over 1 plus t squared dt. And of course, we changed boundaries as well. So the original integral becomes when x is equal to 0, t is equal to 0 as well. When x is equal to half pi, t should be equal to positive infinity. Fine. Now, then x, like I said, turns into arctangent of t. And tangent x becomes t. And don't forget dx, 1 plus t squared dt. And now let me just introduce a parameter, plug b in front of t. And so that gives me 0 to positive infinity. Arctangent of b times t over t times 1 plus t squared dt, and denoted as I of b. Why? Because this is a function in terms of b, because imagine b changes, as b changes, right? For example, when b is equal to 1, that's the original integral, it's going to have a constant value, fixed value. If b is equal to 2, it's going to be a different fixed value. If b is equal to 3, it's going to be a different fixed integral value. So as b changes, the whole integral changes. So now let's look at the derivative with respect to b. I prime of b. And we're going to switch the order of integration. First, I'm going to differentiate inside integrand first, then do the integration. All right. We are supposed to first do the integration, then differentiate, but I'm going to switch the order. Now, since we're differentiating with respect to b, in other words, we treat t as a constant. So copy it down, t times 1 plus t squared. And to differentiate arctangent, standard derivative, right? 1 over 1 plus the whole thing squared, b squared, t squared. And also use chain rule, differentiate inside function, bt. Right now, b is the variable and t is the constant. So just multiply by t, dt. And so therefore we can just successfully cancel out t. Nice. It's very nice, very neat. Now, then I'm going to have a look at, can I split the fraction? Split the fraction. So the reason I can switch the order of integration and differentiation is justified because just refer to any analysis book. For example, the mathematical analysis written by Apostle, or mathematical analysis written by Zorich. The relevant chapters, parametric integration. Right? Long story short. So the splitting the fractions. So first fraction is some constant over 1 plus t squared plus some other constant over 1 plus b squared t squared dt. So what kind of constant makes this equal to that? I would multiply the bottom, then multiply this bit with perhaps with 1. Right? Give me this part, this bit. So what multiplied by this can cancel out with b squared t squared. I say negative b squared. Right? Because that way negative b squared times t squared cancel with the positive b squared t squared. And so I'm left with just on the top I have just 1 minus b squared. Not exactly 1. So how do I turn it into 1? Of course, I divide by one minus b squared. Right? Let's double check that. So 1 plus this bit minus b squared. 1 minus b squared cancel out with this one. So that's exactly that. And so here, of course, I have to require this to be non-zero. So b not equal to positive or negative 1. And so now the rest is easy. The rest is because 1 over 1 minus b squared bracket. The antiderivative of this bit is just arctangent of t. And t evaluated from 0 to positive infinity. Here we have negative b squared. We have arctangent bt. Right? And in order to double check, we just differentiate this bit. That'll give me just standard derivative. 1 over 1 plus b squared t squared. And now t is the variable. So use the chain rule. So I'm going to multiply by b. Right? So I'm going to divide by b to cancel out that b. Divide by b. So it becomes b. Right? Let's just double check that. So differentiate this gives me 1 over 1 plus b squared t squared, fine. And differentiate this bit, b comes out, so b times b squared, fine, no problem. So, and that'll give me 1 over 1 minus b squared times, I believe it's half pi for this bit. And for that bit, I require b to be bigger than 0. Why? Positive b times positive infinity. Still arctangent to positive infinity. Still half pi. No problem. 0. So minus b times half pi. So what if b is equal to 0? Right? If that's the case, I have 0 times arctangent to 0. 0. And this bit is still half pi. And so if I plug b equal to 0, so this will be gone. So I believe b is allowed to be 0. That's fine. So far, I've used substitution to turn the original integral into this same integral, just different variable, a little different format. And here, introduced a parameter here in front of t. So it's a function of, treated as a function of b. And here, I found the derivative with respect to b. Turns out to be this bit, given that b is not equal to positive or negative 1 and it's non-negative. So eventually I'm going to let b equal to 1. But here it says b cannot equal to 1, right? So here's the... So here I'm going to... The reason we cannot allow b to become 1 is because I used splitting the fractions, right? I divided by 1 minus b squared. But before I do that, here b is allowed to be 1, right? This bit is safe. So, in fact, I prime of 1 is equal to 0 to positive infinity 1 over 1 plus t squared, 1 plus t squared, and that's quantity squared dt, right? And all we have to do is to work out. This is easy. This is some standard integration. So t, let me just use t equals trig substitution, obviously. Tangent alpha, right? So dt becomes 1 over cosine square alpha, d alpha. And one plus t square comes inside here. I have 1 plus t square. 1 plus tangent square is secant square. So 1 over cosine square, right? Then square. So cosine to the 4th. And so I prime of 1 is equal. And also don't forget to change the boundaries, right? So when t is equal to 0, alpha equal to 0. T is equal to positive infinity, alpha equal to half pi. So 0 to half pi of dt. dt becomes 1 over cosine square. 1 over cosine square. The bottom becomes this, and flip the bottom, so it becomes that. So cosine to the 4, cosine to the 2. So cosine square of d alpha. Now this is easy. This is 0 to half pi. The double angle identity, right? It's half of 1 plus cosine double angle. And that's going to give me half alpha from 0 to half pi plus half of sine 2 pi. And differentiate that, comes out 2, divide by 2, so 1 over 4. And 0 to half pi. And so that's going to give me pi over 4. And that's sine pi, sine 0, 0, no problem, this one. Right? So this is I prime of 1. Right? So this answers my question. So I was wondering whether b could be equal to 1. Right? So here, simplify this. So half pi, 1 over 1 minus b squared. I have 1 minus b. So difference of perfect square, right? 1 minus b times 1 plus b. So this, no problem. Half pi times 1 over 1 plus b. Right? So really, if here b not equal to 1, but doesn't matter. I use this original bit, it turns out that when b is equal to 1, turns out to be pi over 4. And so here, when b equal to 1 happens to also be equal to pi over 4. Right, so combined together, I can safely say, yes, b could be equal to 1, allowed to be 1. So just not equal to -1, right? Non-negative, not equal to -1. But combined together, this is just useless, right? It's already non-negative, so this is already doesn't matter, right? So this is the restriction. So now we've just found the derivative of I of b. In other words, I prime of b happens to be this bit. And b could be equal to 0, could be equal to 1, right? And so now I'm going to determine the I of b, right? Since derivative is equal to that, so its antiderivative would be the indefinite integral of that bit, half pi, 1 over 1 plus b, db, right? And so that's half pi taken out, 1 over 1 plus b, easy, just log of 1 plus b, and of course plus constant. So how do we determine the constant? So we can just say, okay, let me just look at I of 0. Now plug 0 into here. Arctangent of 0, just 0. At the same time, so b0 plug in here, right? Plug in here. So log of 1, that is 0, right? C is equal to 0. No problem. And finally, if I let b equal to 1, that's my desired goal, right? B equal to 1, the original integral, that bit, right? So I is just I of 1. That is just plug 1 into here. Just half pi times log of 2